let me give you the basics of a transformer. Okay, the transformer is really for the first time implemented by Tesla in this three-phase system, and worked also in a single phase, is something that has to have inductance. In fact, if you go back and most of you saw, at least you've seen my recorded lecture, and I explained there how even Faraday didn't get to it. He came with his much wider law of electromagnetic inductions, but it was never really thought of as something that will come up with a new component, which I would, let me see if I can move this down. Yeah, I can move this down here so I don't, and I can take draw. There is a more attractive red color, right? Agree? Okay, so now this was what was missing, an AC inductor component, which was indirectly invented by Faraday, but only as a, electromagnetic induction. You cannot change impedance and so on. But really, once Tesla came up with the alternating generator, you see, with a sinusoidal voltage, which automatically has a volt-second balance, positive and negative volt-second balance. So there is no DC current introduced here. Why I say that is important? Because I mentioned last time also, it is fortuitous that his AC generator, not only single phase, but more important, two-phase and three-phase generators, have a satisfied automatic volt-second balance that there is a zero average. This positive and negative areas are identical. There is not even a minute difference. When I started my company in 1979 and we made the first 4 kilowatt photovoltaic inverter, we had to make sure when we had output, which was rectified sine wave using any push-pull or any other bridge-type converters to have rectified sine wave, and then we used the so-called active bridge to unfold it into the positive and negative part. Active bridge is 60 hertz, so that way you use high frequency to generate modulation, and then unfolding stage with the active switch, 4 active switches to unfold it. But you have to make sure that there is no DC average. Why? Because if you put that now, after this, you put that to 60 hertz transformer, 60 hertz transformer wouldn't like any minor DC current because it will be short. And you don't want to have a short instead of a big impedance. So that is one thing. So basically what happened is this was automatically provided that you have here the, let's see, why? They don't give me now. Where is my choice of a color? I want to get a blue. I love the blue, Okay, I'll have to live with the green. So there is this current here. And this is impedance, inductance. So let me, what is the Faraday's law? Last time I showed you that flux N times V is flux linkages. If you have a coil, the number of turns N, each turn contributes a flux P, and the total flux seen by the end of the coil is N times P. That's flux linkages. And I showed you last time how you can go from V to versus H, point properties of ferromagnetic materials. You can get to device properties we described for particular core and particular cross section and particular lengths of the core, come up with the inductance times the current going in the core, L, I, L, and flux. And you know, replace this here, N times 3 is Li, and what do you get? V is L di per dt. Okay? So now you have the voltage, what you're impressing on it, you're impressing it on the quantity called inductance, but this is an AC inductor. And then if this is L di per dt, and if the voltage is sinusoidal, what is the current? Integral of V dt, integral volt seconds. And if the voltage is cosine omega t, this current is a sine omega t. So you see what I'm saying? Everything is time domain. But now let's talk about transformer. How do I build transformer out of it? Let's see, where is my draw? And I have these things. So now, okay, let me remove this from here so I have a space and draw. And I use black. So here I have a driving voltage, and this here, this is what they call, you know, electromotive force and so on. But we now talk about circuits. So let's continue about circuit. So this is that AC inductor, right? And now put a voltage source here, and I'm going to generate the current, which is what? If this is voltage source cosine, the current is going to be sine. Shifted 90 degree, cosine, sine, right? This starts at 0, this is sine, and this is cosine. And that's the problem of understanding the transformer. The current going, this inductance is actually, if this inductance is very large, and this inductance will be very large if you have put this inductance on iron core, which is ferromagnetic materials, which has a magnetic materials, not magnetic materials, silicon steel, which has 100,000 relative permeability. So that means this inductance is going to be huge and create very little current. But that is that current which will create the flux in the core. So now if I put a core around it, magnetic core, this small current will generate the flux in the core. And flux in the core according to the same law, V is N 2 dphi per dt. There is only one flux in the core, the same flux that will be generated by this small current, which we call magnetizing current. If I put now on the secondary side another winding with the same number of turns, N, like it was here, N, I will replicate this voltage on here. And of course, if there is no load put on this output, there'll be no difference. You have an induced voltage here and you have induced voltage here. Same voltage, same flux current, but small current in the primary is going to create all the flux in the core that you need to generate the secondary voltage, and secondary voltage is isolated electrically. But that's not the point. That's the same thing happening in the flyback converter. It has a primary and secondary isolated. It has a turns ratio. You can step up and step down voltage. But that's not the point of a transformer. Point of a transformer, it does not store energy. Why? Because the same small magnetizing current here that I showed you, it'll fly whether you put here the resistor, whether you put a small resistor and large current, you will have now this voltage, which is identical to input voltage, will start driving the current into this load. You agree? And driving the huge current. Why do I put the dot connection here? To satisfy, to reflect understanding of transformer that it is essentially dot connection designates when you drive one winding and put it at the point where it is positive drive, like here, positive sine wave voltage. I put it on a other winding which has the same voltage in phase with this voltage. I put a dot connection. What is the significance of dot connection? When you start drawing the current, there is a voltage source here which is driving the voltage here. But that voltage source here requires that the current on the input is going to go this way. So if I show these two windings, but really this primary, these are two windings of a transformer like turns ratio, but really, as I explained, this is an AC magnetizing inductance, which is on a primary. So what happens? The secondary current is coming out of the dot. It's coming here, reflected here is coming this way. And input current is also coming into the dot because that's a driving winding, driving this here. So what is the current in this magnetizing inductance? Difference between input current minus output current, reflected output current, which is the same small magnetizing current due to that AC inductor. You get it? That is important. That's most important. That's the transformer we need to build in the switching converters, and not the transformer with the concoction of the full bridge primary side, 4-diode secondary side. It doesn't satisfy requirements that the transformer need. Volt-second balance or flux balance and charge balance, okay? What is the other thing which is not being recognized in the present converters? What you're always going to see is, the transformer, 60 Hertz transformer, was ideal device used for impedance matching, right? If you had here speaker, and speaker is designed to have 8-ohm impedance, like standardized. But if you want to transfer from AC source, music or whatever, maximum power to the secondary side, you can derive equation which will basically say the source impedance has to match the reflected load impedance. And that how you can match this impedance, which you don't have a control. You can use the turns ratio of the transformer and match it for maximum power transfer to speakers. But turns ratio does one more thing in the switching converters, not in the 60 Hertz transformer. It does automatically transfer of a secondary side to primary side, and with the turns ratio changes the voltage stresses and current stresses on devices. So if you have a 10-to-1 step down from primary to secondary, secondary devices should have a 10 times smaller voltage, but 10 times higher current. And primary devices, likewise, if you have a 1 volt on the output and 10-to-1 step down, primary will have now 10 times higher voltage, but 10 times smaller current. But is that used in the switching converters? No, because we often do one wrong thing is we think what's important is to use a duty ratio of the converter down at 0.1 so we can step down with the duty ratio. That's wrong. If you do that, you're going to be stuck with the high voltages devices on the primary and high voltage devices on the secondary. Okay? But that's also another thing, that the way transformers are being done is just not right, because none of them are really true AC transformer. We can go and give you a full lecture over why the forward converter is not beautiful. Yes, it has a transformer look-alike, but it is a fake transformer because It cannot operate continuously like here. AC line, you operate for positive flux, and for negative flux, you transfer the power to the output, right? Now, let me tell you one thing. Let's go now to why everything looks much better now. Would the transformer change its operation if I drive it instead of a sine wave voltage, if I drive it with a square wave voltage? What do you think? Would it matter whether it has a square wave or any time varying waveform which has a zero average, in fact? But simplest one is the square wave. So let's look at it. Here is a transformer with the turns ratio. Let's call it 1:1, whatever it is. But let's drive it now with the square wave. Now things get simpler to understand from a standpoint of power. Square wave voltage here, right, is going to generate, would you agree, with 1:1 turns ratio, it's going to create a square wave voltage here. Now, if you have a resistor, whatever value is, it'll create square wave voltage here, it will create the square wave current here, right? That square wave current here will reflect as the square wave current here, and therefore there will be square wave current on this side, like here, and so you have square wave voltage here and square wave current. So you have.
What do you need? Never mind, I wanted to show you the thing I made last night, but it's alright. I'll show you after.
You have a square wave current, but this voltage here will create also what kind of a current? Square wave voltage divided by this inductance will create triangular current. Remember, that's that magnetizing current now becomes triangular with a zero average. Remember, that's the current I was telling you. If you do simulation in a Plex and some others, make sure you have an inductance associated here. And when you get the waveforms of that inductance, make sure that it has a zero average, because then it is proved that this transformer is an AC transformer. Now, when you have this triangular current and reflected square wave current together, what is going to current on the input? The input current, I wish I had a different color here, then let's say I'll still use it. Then this square wave current reflected on the primary plus triangular current here, these two currents will add to get together to the current which has a square wave part plus some triangular part on the other side, right? So the point I'm going to make now is, what is the power, input power, time domain, and output power? Square wave voltage V and current I, square wave, and minus V and minus I. Here is the main point, the same thing that happens in a 60 Hertz transformer, except there is a sine wave voltage and sine wave current out of phase. But here you see clearly that the voltage product of instantaneous power, voltage and current, is a constant VI. You agree? And then negative voltage and negative current is also VI. Do you agree that it's constant? So there is no fluctuation on the power on the output when the square wave is driven. What about input side? It would have at this point, when not including this here, here it will be voltage times square wave current. It'll be same VI. You agree with that? So input power and output power will be the same. So if this magnetizing inductance is high and a 60 hertz transformer, it is high. It is 100,000 times more than the inductance on a free space. So this is huge. This is milliamps or amp or current for hundreds of amp of input and output. So if that is the case, basically, ideally, if you assume that it's infinitely large, constant input power and constant output power, no energy storage. You got it? No energy storage in device. But if you take into account this triangular current, you multiply this red with the square wave here, what you're going to get? You're going to get this sawtooth-like waveform, which has the same average VI and has a ripple at the top of it. Now, do you say that's storage? No. AC inductor doesn't store energy. This AC inductors just go from storing energy inductance during on time and releasing into your off time back in the circuit. So it's a circulating current. This magnetizing current is circulating current, which enables the magnetic core to have a flux in it and to generate. So, point being, go back to 1879. That's where Maxwell died. Maxwell came up with his famous Maxwell equations. Beautiful. And it's almost, amazing how he came up with the theory before even transformer was used. Like Tesla, 3 years later, in 1882, came up with the AC generator, AC transformers, 3-phase, and so on, in the AC induction motor, and so on. But it was amazing that Maxwell came up with equations. Do you know that famous four Maxwell equations are not really Maxwell's equation? Anybody knows why? Because Maxwell wrote this equation before vector calculus was invented. And his four Maxwell equations were written in three coordinates, x, y, and z, and written in the form of 22 partial differential equations relative to x, y, and z, and second order partial differential equation relative to x, y, and z, and second order partial differential equation in time. And out of this whole concoction, he added one additional term, which was a moving current in a capacitor, and we determined that that has to be, when that is made zero, his partial differential equation somehow can be separated in a separate equation. And here comes his beautiful theory that there is electromagnetic, he gave a credit to Faraday for saying there is an electric field everywhere, unlike the Newton's that gravitation happens and there is nothing, dead space and so on. There is no effect of the media. And he proved and came up with a conclusion that 1 over square root of epsilon 0 and mu 0 is the speed of light. And these are two constant in vacuum, permeability of free space and permeance of the free space. And you take this, and at that time they were determining what the constants are and calculate the speed of light. And it turned out it's not the speed of light, it's speed of all electromagnetic waves, those visible and not visible. So who came up after that? Many years later, there was a guy who invented, he applied vector calculus to his 22 partial differential, second order partial differential equations to come up with four vector form differential equations. Okay. So anyway, this is, but the point I'm trying to also make is, you see, you go out in internet, you'll find out the people, tie themselves in trying to explain how the transformer works and so on, because they go look at the Faraday's law and look at all other ways how you can induce a voltage, not only by moving magnet and but changing the geometry of the circuit and changing the flux, magnetic flux, getting in certain angle to loop. So all these three methods, but they confuse the. This is a static device, which when for the first time here we have seen why the inductance is very important and why inductance has to be an AC inductor. And don't, you know, at the Faraday's time, of course, what do people use? The turns ratio, and you use the DC source, and you use a switch. And the moment you turn the switch on, there is a transient, and transient will generate in a secondary side. If you have here the meter, decline of the meter, if you turn it off and turn it off. But it took them 50 years to figure out that really the objective of is to have an alternating current and alternating voltage and not this transient. And of course, a transient could be the high step-up voltage, generate a high voltage spike and kill someone, you know, but that's not a point. You had no use for it, you know, and everybody claimed that there is no use for it because you couldn't, in fact, some 30, 40 years after Faraday, some people came up and Edison came with this Edison bulb and say, oh, we can drive the Edison bulb, didn't care whether it was a DC or AC drive. But the point I'm making with all of this power transfer another property of a transformer is power transfer has to happen for both parts, positive and negative. As you saw here, positive voltage and positive current, negative voltage and negative current, and you see clearly how the magnetizing current is in phase. Magnetic current is in phase of driving voltage. That was difficult understanding transformer driven by 60 hertz because magnetizing current is 90% phase shifted with respect to the voltage and with respect to the input and output current. So therefore, you had to add up two currents which are 90 degrees out of phase. Of course, one of them, magnetizing, is very small, but nevertheless, it was mentally difficult for people to understand what's going on, okay? So anyway, that's the story of transformer, and I hope this kind of puts the closing picture of it. If you had, now it's 1 hour since we started talking, and probably, usually I do have, let's say, 10-minute breaks typically, but this is not typical lecture. I give you opportunity to, let's say, shut it off. And I'll put it now on gallery view. And now you can have for next 10 minutes or 5 minutes, have a question on audio, and if you want to show your face on video too, asking any question related to what I covered so far. So then we can move on from here.